Okay, so let's talk about my whisper experiments and what I'm going to be doing to improve them. So very briefly, what is whisper? Well, it's a weak signal propagation reporter network where there's receiving stations all over the world just listening on particular frequencies at particular times, and any signal received is sent near real time to a central database. And if you interrogate this database, it'll provide information about where your signal's been received, i.e. I've been heard here and at what time and at what signal strength. This allows the transmitting station to analyse the antenna performance and RF propagation on that day at that time. So that's a very brief explanation of whisper. I won't go into any more details, but suffice to say, with a very basic system, which this is the system I'm running at the moment, so I'm using the Simple VFO hardware, which I described in a separate video which I'll link below, and loading different software onto that hardware. I can use the RF output from the SI5351 feeding into a small Class D power amplifier and out to the antenna. Now, running 2 to 3 watts into my antenna from this system, I'm able to get out a pretty long way. I'm able to get out excuse me, all across Europe, into Iceland, down into Antarctica to a research station down there, east coast of America. That's pretty impressive when you think about it. 2 watts, which is, the equivalent power of a tiny little pen torch, into a modest antenna, and I'm running a 175-foot delta loop at an average height of about 30 feet. So it's a very modest antenna. So 2 watts into that antenna using this weak signal propagation system, that I think is pretty impressive performance. But I want to improve my current system to be able to vary the output power at different time slots with the software. So what I want to do is, using the same Simple VFO hardware and the Whisper software, I want to feed the RF into a digital attenuator where I can vary the output, vary the power into the power amplifier, and thus vary the final power into the antenna from very small power, let's say a quarter of a watt, up to say a maximum of 3 watts. And ultimately I want to control that power amplifier and implement the Raised Cosine transmit profile envelope, which I developed for the CW rig. And again, I'll post the link to the video describing that. But for the rest of this video, it's not going to be a death by PowerPoint slides. I just want to concentrate on this section of my developments. So initially, I need to look at the requirements for this digital attenuator. So as I mentioned before, quarter of a watt up to say a maximum of 3 watts. I'm looking at a range of around about 14 dBm. Now 14 dBm control here will then vary the output of this to the range that I'm looking at the final output power to the transmitter. So we've got our range, so the attenuator needs to cover 0 to at least 14 dBm. Okay, so we've got the range required for our digital attenuator, so we want a range of between 0 to say 15 dBm. Well, we also need to make sure that the hardware can control whatever device we select there. So just have a double check on the hardware. Now, you won't be able to see this very clearly, but this is the schematic of the processor board for the Simple VFO hardware. And I've got a connector here heading out onto the back plane, and I've got 3 pins connected to the teensy, which I can use to control a device. And note, I'll also need a DAC output from the teensy to feed the power amplifier eventually. And fortunately, I've taken that DAC output to the rear header as well. So the hardware will cope. We just now need to look at devices for the digital attenuator. Now, in my junk box, I had one of these, and it's based on a P43703 digital attenuator chip. Now, I bought this for a project, and it's been in my junk box for well, I can't remember how long, at least a couple of years, and I've never actually used it. So, pulling the data sheet out from that, this supposedly gives me a range of 0 to 31.75 dBm in 0.25 dB steps. So ideal, really. And it's serial controlled, so we've got data clock and enable. Perfect for hooking up to the Simple VFO hardware. So we were in business. Well, I thought we were. I spent many hours trying to get this wee beast to actually work, and I was getting nowhere. Couldn't understand what was going on. Failed to get well, it just wouldn't do what I wanted it to do. So out of desperation, I eventually unsoldered the screening can, removed the screening can from this Chinese breakout board, and lo and behold, the attenuator chip, I don't know whether you can see that, is missing. So obviously it wouldn't work. So that was 20 quid wasted. So what to do next? My mind started to think about the ultimate solution, where I'd be making a dedicated bespoke PCB. And if I was going to be using a chip this sort of size, and no, this chip is tiny. If you have a look at the data sheet, it's 32 pins, and it's a leadless package. So putting this into perspective, on each side there's eight pins, and so there's 8 pins to solder in a 3.5 millimeter length. So it's tricky. And I'd never actually hand soldered one of these small devices before, so I wanted to try different techniques of soldering that. So I ended up designing my own breakout board, and it ended up looking like this. So this is my breakout board. I've got serial and parallel interface to it. I'm not actually using the parallel interface. I can use these jumpers to change the change the address selection to the chip, and I could then try various techniques of actually fitting the chip, soldering the chip to the PCB, and to try and make it as best performance as possible. I ended up running to a 4-layer PCB, and I've maintained 50 ohm tracking between input and output. I've got a dedicated ground plane underneath, and everything seems to be fine. So that's my new breakout board. So the next challenge was to develop software to talk to this device from the Simple VFO hardware, and to test it. So that's what we're talking. So when it came to actually looking at the specific device, the device that was used wasn't used in the Chinese breakout board, I discovered was now obsolete. So maybe that's why it was missing. I can't comment. However, the manufacturer, Peregrine Semiconductor, recommend this device as a drop-in replacement. It's got exactly the same features, where I can set the device address down here. If you remember, I had jumpers on the hardware to do that. It's got a parallel interface, which I'm not using, and a serial interface, which requires 3 pins, which I've got available from the hardware. And by setting these 3 pins with the correct address, I can then vary the attenuation that's being applied to the RF input and the RF output, which is great news. So this is the device I intend to use, and it's the device I purchased and soldered on my breakout board. And if we look a bit further down the data sheet, we see the addressing requirements to set the address word on the jumpers. It talks about what the attenuation word looks like for different attenuation, and it also gives us the format of this attenuation word. There's a 16-bit serial input to the device, so we need to squirt from the teensy 16 bits of data at the right timing in the right sequence. It's made up of 2 8-bit words. We've got the first word is the attenuation word, and the second word is the device address, and it's clocked into the device least significant bit first. And if we come down a bit further, we'll see some timing information, where we've got the enable pins, the clock pins, and then the serial data. So the attenuation bit, least significant bits, pumped into the device first. So these 7 bits dictate the amount of attenuation. Bit 7's ignored. No, it's not. Bit 7 must be held low. The next 3 bits dictate the device address, and the next 5 bits, it doesn't matter. So I needed to generate a little bit of software to implement this on the Teensy. So I chose to use the Simple VFO hardware as the test platform. Might as well. I'm going to use it in the end. At the end. So I've got a sketch here that. Well, I'll show you it in action, but in a moment. But the main guts of it really is this this section here, where these are the 3 pins that I'm playing with. Output to the rear header on the hardware. I've selected to set the address at 1, and I've matched the jumpers on the hardware to suit. And then I've just got this very, very simple block of code which sets the level attenuation word in first, so shifts out least significant bit of the value that's held in that register, followed by the address, which is hard coded up here, and then I toggle the LE. So that little bit of section of code, when run, should squirt this data into the chip, setting the attenuation word. So I'll now jump back to the hardware and show you what that looks like on the Simple VFO hardware. Okay, so running this test software on the Simple VFO hardware, you can there's 2 areas of the screen. There's the attenuation value, which is the stream I'm sending to the digital attenuation chip, and the frequency that's coming out of the SI 5351, and I can change that frequency by the usual methods to any desired frequency. But to make it a little bit easier, if you push the encoder button in, it jumps to pre-programmed whisper frequencies. Once you've selected that, up and down buttons to select the attenuation, which you can then change, and in each change the data stream should be sent out on the 3 pins onto the backplane. So that's the test software. Now before I hook it up to the attenuator, I want to analyze those 3 pins to ensure that I'm getting exactly the correct clock sequence from those pins. And the way I test those signals for a project like this would be with a logic analyzer, and this is the one I use. Very, very cheap. I think it was like £10 from Hobby. Was it Hobby Components? Yeah, Hobby Components. And with this connected to the computer and wiring it up to the header on the back of the Simple VFO hardware, I'll be able to analyse the clock signals and the clock train on the computer and double check to see if the software is working correctly before I hook it all up to my a digital attenuator breadboard. So we'll look at this this software next. A logic analyzer, I was right, it was £10 from Hobby Components. Now that's the hardware, but obviously you need to interface that with some software. And luckily for us, it works with SIGROC. Now, SIGROC is an open source platform for analysing signals from logic analyzers, oscilloscopes, and much, much more. Extremely powerful piece of free software, and it's available for most operating systems, well, Unix, Windows, Mac. Yeah, fantastic. I'll show you in action. I'm not going to give you a tutorial about how to use it. There's plenty online, but I will show you the results from my little experiments here. Pulse view session set up. It's connected to my logic analyzer. I've set it for 20 million samples at a rate of 24 megahertz. So that's the capture duration. I've connected 3 pins to the Simple VFO hardware. LE, which goes to pin 22, clock goes to pin 6, and data's pin 5. And I've got the Simple VFO hardware set at 0 dB. So when I hit this run button, I'll rotate the encoder, which will increment the attenuation value, and we should see a series of pulses which we can zoom in and analyse, and hopefully see something like the datasheet's expecting. So let's give it a go. So hit run, and there we go. Now each of these pulses I can zoom in on. Let's start on the first one. Let's zoom straight in onto that, and I can see the clock train. I can see the attenuation word, which is the first 8 bits, remember, followed by the address word, which I've set at 1, which is set there. So it looks like my software is generating exactly what I want to see. So let's have a look at the next pulse. Zoom out and then zoom in. Bearing in mind I was incrementing the value, so the attenuation word should increase, which it has done. And if we go back to the data sheet and have a look at the attenuation word with the second bit high, which is there, and the first bit low, I'm requesting half a dB there. That won't change because that's the address bit, and that's clocking the output direct. That's the LE clock. So everything's looking good. So if we now move out, zoom out, and then zoom in, you can see bit 0 and bit 1 are high, which is what I expected because I'm incrementing the count. And zoom out, and then zoom in, So everything is working as expected. So the software is working, brilliant. Now I think this video is long enough. I think I'll have to do a part 2 when I'm hooking up the breadboard attenuator to the PA, and we can start measuring the output of the PA and varying the attenuation, and we'll be able to see what's going on from there. So I hope you've enjoyed this video. It's been a bit long-winded, but it shows you my method of breaking down a problem and testing individual solutions as I progress to a final solution. So happy home brewing, and I think I'll call it a day on this one.